Hi, folks. How y'all doing? We are wrapping up chapter 3 today, and let's just go ahead and get started. So, we've talked about column spaces, we've talked about linear transformations. We're going to talk about a short little thing that will connect them together a little bit. Um, Let A be any matrix, it does not have to be square. Um, and we're going to build a linear transformation using A as the matrix of the linear transformation. The column space of the matrix is the same as the range, and this is range is in like domain and range. It's the output of the function t. Um, so I have an example here. Let's let A be this matrix here. Um, so let's think about what's happening here. If I start with a vector in R2, um, so my input vector, I'll use, let's say, 3, -1 as an example, then the transformation of 3, -1, the transformed version of 3, -1, is A times 3, -1. And this is the linear combination where we use 3 and -1 as weights for these columns. So 3 times 1, 0, 0, plus -1 times 0, 0, 1. Or 3, 0, -1. And this is our output vector. And so what's happening here is that the vector 3, -1 in R2 transforms into the vector, and now we're in 3 dimensions, x, y, z, 3 on the x direction, 0 in the y direction, -1 in the z direction, so it's this vector down here, 3, 0, -1. And you can kind of imagine what would happen to some other vectors if I change the input around. I'm just changing the weights. So the vector 2, 4 becomes 2 times 1, 0, 0, plus 4 times 0, 0, 1, becomes the vector 2, 0, 4, which is 2 units over, 4 units up, becomes 2, 0, 4. And in general, the two-dimensional plane here gets transformed into the two-dimensional xz plane inside three-dimensional space. And so the range is the xy plane. But we can test this using column space also. The column space of A is by definition the span of the columns 1, 0, 0 and 0, 1, 0. I'm sorry, 0, 0, 1. We get that right. Which is the set of all combinations that have a x coordinate, a 0 for the y coordinate, and then something for the z coordinate. And so that is also the xy plane. And so our big takeaway from here is that we have an easy way of calculating the range of a linear transformation. It is the span of the columns. It's the same as the column space. And so the column space of A is equal to the range of the linear transformation T that is based on the matrix A. All right? All right. One more thing. We have talked about column space. We've talked about null space. We haven't talked about row space yet, but there's nothing new to row space. Rows and columns are what we get when we transpose a matrix. The row space of a matrix is just the same thing as the column space of the transposed matrix. So in this example, if I want to find the row space of this matrix, the row space of 1, 2, 4 going across 1, 3, 7 is the same as the column space of, now 1, 2, 4 goes down, 1, 3, 7 goes down. I've transposed the matrix, and so that is the span of the columns 1, 2, 4, 1, 3, 7. That is the row space. Da 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 da. That's all it is. Is we just take the matrix, and instead of taking the columns, we take the rows and we write them vertically and put the span in front of it. We'll do one more example of row space. This is the answer to the example we just did. Row of A is column of AT. So the column space is 1, 2, 4 going down, 1, 3, 7 going down, and it's the span of those two vectors. That's already in your notes. Here's the other example. Find a basis for the row space of A. Well, we know that this that the row space of A is the span of the vectors 1, 2, 4, 1, 3, 7. A basis must be, by definition, linearly independent. And that implies that there must be a leading entry or pivot in every column. Do we have a pivot in every column here? Well, yes, we do, and it's pretty easy to tell. We just have to row reduce this a little bit. But I think you can kind of do enough in your head to convince yourself there will be two pivots here. If I cancel the 2 and I cancel the 4, this is 2 row 2 minus 2 row 1, and row 4 minus 4 row 1. That's 1, 1. 2 minus 2 is 0. 3 minus 2 is 1. 4 minus 4 is 0. 7 minus 4 is 3. And then get rid of this 3. Row 3 minus 3 row 2 is 1, 1, 0, 1, 0, 0. And yes, indeed, we have a pivot in both columns. And so the basis does not include the word span, remember. The basis is just a set 1, 2, 4, 1, 3, 7. So basis has to be linearly independent. In this case, the set is already linearly independent, but the basis does not include the word span. All right. Let's move on to one more topic, and then we're going to wrap up the chapter. We're now focusing again on square matrices. So this is a square matrix. And I'm going to show you 10 statements, and we want to talk about which of these statements is equivalent to the statement that just says A is invertible. By definition, invertible means that we have a pivot in every row and every column. So which of these are equivalent? Number one says that we have a linearly independent set. Well, we know that linearly independent means it's a pivot in every column. But since the matrix is square, having a pivot in every column also means that we have a pivot in every row. And so just saying that the columns are linearly independent, these two statements are equivalent. So if I tell you, and I know that if I know for a fact that the matrix is square, and I tell you that the columns are linearly independent, that's enough for you to conclude that the matrix is invertible. So what if I tell you the columns form a spanning set? Well, spanning set for Rn means that there's a pivot in every row. But again, because the matrix is square, when we finish up all the rows, we finish up all the columns, and therefore being a spanning set for Rn is equivalent to being invertible. These are also equivalent. I'm not going to be able to spell that word today, am I? Equivalent. We'll do a few more. They get harder as we go. Number 3 says that the homogeneous equation has only the trivial solution. Well, we know that the homogeneous equation always has a trivial solution. That is, if I set my weights equal to 0 in the linear combination, 0 times a vector plus 0 times a vector plus 0 times a vector adds up to 0. But if this is the only solution, that means there's no freedom in the system. This means there are no free variables. If there are no free variables, then we must have a pivot in every column. And because the matrix is square, having a pivot in every column means the same thing as having a pivot in every row. And so these statements are equivalent. So if I told you we had an n by n matrix and the homogeneous equation has only the trivial solution, that's enough for you to conclude that the matrix is invertible. Here's another one. The equation ax equals b is consistent for all b. So that means no matter what I put in the augmented column, the system will always be consistent. That means we can never have a pivot in the augmented column, and that's because in the coefficient side of the matrix, we have a pivot before we get to the augmented column in every row. This can't be a pivot because we already have a pivot in this row. This can't be a pivot because we already have a pivot in this row. And so on and so forth. That means we have a pivot in every row of A. And again, because A is square, having a pivot in every row and having a pivot in every column are equivalent. And therefore, we have a pivot in every row and every column. And so this is invertible. And so this statement is equivalent. Let's keep going. If the determinant of A is non-zero, so we did see a shortcut for the determinant of a 2 by 2 matrix that requires dividing by the determinant. But importantly here, we know that in echelon form, the determinant of A is what we get when we multiply going down the diagonal. So it's the product of the entries along the diagonal. But if the determinant is non-zero, that means that this cannot be a zero, and this cannot be a zero, and this cannot be a zero. And that means we have a pivot in every row and every column. If the product does not equal zero, then no entry on the diagonal is zero, and so we have a pivot in every row and column. And so this is also equivalent. If I tell you that the determinant of a square matrix is not zero, then you automatically know that the matrix is invertible, because those two statements are equivalent to each other. Number 6, A is row equivalent to the identity matrix. That is, if I were to take the matrix A and row reduce it, I would get the matrix that looks like the identity matrix for whatever size A is. Well, if that happens, then we have a leading entry in every row and every column, because that's what the identity matrix looks like. I say leading entry, I could also say pivot in every row and every column. And so this is equivalent. All of these are just different ways of saying the same information, that A is invertible. Number 7, the rank of A is n. Well, the rank is the number of pivots. And if the size of the matrix is n by n, then the pivots have to occupy every row and every column, because I can't have two pivots in the same column. And so this is equivalent. Few more, let's keep going. Number 8, the nullity is 0. The nullity, this is a term we defined in the last video. The nullity is the number of columns without pivots. So it's complementary to the rank. And if the nullity is 0, then every column has a pivot. And so these are equivalent. All right, number 9, the column space of A is all of Rn. Well, We know that the column space is the span of the columns. And if that span is equal to Rn, in other words, if the set of vectors in A is a spanning set for all of Rn, then that tells us that there is a pivot in every row. And if there's a pivot in every row, then the matrix is invertible. These are equivalent. Saying that the column space is all of Rn and not a subspace of Rn is equivalent to saying that the matrix is invertible. So the last one, the null space of A is just the set containing the zero vector. That is, it's not the span of any other vectors. So that means that in the matrix A, I can have no columns that contribute to the null space. So when I augment A with 0, and I row reduce, none of these columns will be free variables that I can put an S in front of or T in front of, and then have a vector that would contribute to my null space. And that means that this column is not free, and this column is not free. And however many columns we have, none of the columns of A are free. But if none of the columns are free, then we must have a pivot in every column. And therefore, this is another equivalent statement. So we've seen 10 completely different ways of saying that the matrix A is invertible using the language of linear algebra to convey this idea that we have a pivot in every row and every column using different concepts. All right. I hope seeing all those equivalences was helpful. We will start a new chapter in the next video. Thanks for watching.